Hey guys. So today's question is going to be talking about baseball. It asks, the fastest pitch baseball was clocked at 47 meters per second. If the pitcher exerted his throwing force, assumed to be horizontal and constant, over a distance of 1 meter, the baseball has a mass of 145 grams. Draw a free body diagram of the ball during the pitch. What force did the pitcher exert on the ball during this record-setting pitch? And estimate the force as in part B as a fraction of the pitcher's weight. So when drawing a free body diagram, for this case, it's important to keep in mind that normally a pitcher, when they throw the ball, they aren't throwing it perfectly horizontal. Otherwise, the ball would just hit the floor before it reached the batter. But in this case, they want us to assume that it's horizontal. So when we're drawing the free body diagram, we'll assume it as such. So we have the baseball, which we'll draw it as just a little particle. We have the force of gravity, which is always going to point down. We'll note that as G. It's still in the pitcher's hand, so there's normal force acting parallel to his hand, and we'll assume that it's going to be straight. We'll note that as N. And then we also have the force of his throw. Again, we're going to assume it's horizontal. Not sure how accurate this is to real life, but in this case, it'll work. And we'll actually note that as the force of the throw. Secondly, it's going to ask us to calculate the force, and so we have a few important variables that we have to work with. We're given a velocity of 47 meters per second. We have 47 meters per second. We have a distance of 1 meter. We'll write that right here as 1 meter. And then we also have a mass of 145 grams. We don't usually work in grams. I'm actually just going to convert that to kilograms just by moving the decimal place a little bit. 145 and kilograms. Now, we're also going to assume that the initial velocity is 0. So to calculate the force, we'll go ahead and use this formula. It's going to look like the force times the change in distance is equal to 1/2 meters times velocity squared. And we're trying to isolate the force, so we'll go ahead and divide by the distance on both sides, and that will cancel out. So we have force is equal to 1/2 mass times volume squared divided by change in distance. And we actually have all of these variables. Now from here, it's pretty much plug and chug. We have force is equal to 1/2 of 145, it's an ugly 5, 145 kilograms times our velocity, which we know is 47 meters per second, again, ugly S, meters per second, and squared. Always write the units. We're also going to have a distance of 1.0 meters. Now, when we calculate that, we get a force of 160.15 newtons. Okay, and that's actually going to answer our second question. Now, this problem doesn't directly ask to solve for acceleration, but just because it's good practice, we'll do it anyways. So normally we have an equation that looks like this. It's going to be the net force is equal to mass times acceleration. We want to isolate acceleration. We're going to divide by mass on both sides, and we get acceleration is equal to net force divided by mass. And we actually have all of those variables now. Our net force is going to be 160.15 newtons. We're going to divide that by our mass of 0.145 kilograms. And that gives our acceleration a value of 1,104.5 meters per second squared. This is a huge number. We'll actually simplify it to be like 1.10 times 10 to the third meters per second squared. It's getting kind of messy. We'll actually write that up here as well. Perfect. Now the second part of the question is asking for the force as a fraction over the weight. We're not given any information about the pitcher's weight, so we'll actually go ahead and estimate it and say that he has a mass of 80 kilograms. He's not super big, he's not super small. And now if we're given the mass and we want to get to the weight, we're going to use the formula weight is equal to mass times gravity. And when we plug and chug that, we're going to have 80 kilograms times 9.8 meters per second squared. And we get 784 newtons. This is a good number to work with. Now, if we're going to calculate it as a fraction with force over weight, we know our force is 160.15 newtons. And then we have a weight that we just calculated as 784 newtons. It's asking for a fraction, and fractions don't usually have units, so we can cancel that out, and we get 0.20. Now, if we multiply it by 100, we can get it as a fraction, and we get roughly 20%, and 20% as a fraction is 1/5. He's using 1/5 of his body weight. Quite a lot, actually, but yeah, I hope that helped.